Hello everyone, this is chapter 11.8 where we'll be discussing power series. And the first things I want to get out of the way are basically some vocabularies regarding power series. So a power series is just a series of the form of this. So basically we have coefficients and powers of x starting with 0 and then to infinity. So C0, C1 times x, C2 times x to the 2, and so on. Basically what the power series does is it mimics a polynomial, but it's an infinite polynomial now with infinite degree you can think of. And for that reason, we always write it in this kind of ascending order. So start with a constant, then linear, then quadratic, and so on. Now, a power series centered, so-called centered at x equals a, is just a power series, and instead of x as being our base, we're going to have x minus the center a. So notice here, we have C0 times x minus a to the 0 is just, well, it's just 1, so that's just C0. C1 times x minus a to the 1, C2 times x minus a to the 2, and so on. And now the interval of convergence of a power series is the set of all x values for which the power series actually converges. And let me say as a note here, let me do it in a different color, like red, I guess. Just as a quick note, here we'll be very often using ratio test. But let me just say that when you use a ratio test, basically we want to force convergence. So we're going to see when x converges, for what value of x the power series converge. We'll see examples of that in the next screen. But we want to force it being less than 1 because that's when the ratio test actually concludes convergence. The only problem is the ratio test is inconclusive when it's equal to 1. So let me also say that we have to test the endpoints of the interval of convergence. And again, we'll actually discuss this in more detail with later examples. But for right now, this is what I have to say. And then beyond interval of convergence, there's something called the radius of convergence, which is just denoted capital R. And it's basically half the length of the interval of convergence. So for example, if the interval of convergence is negative 2, 4, well, then in that case, the length of this interval is, notice it's just 4 minus negative 2 is 6, and half of that distance 6 is 3. So the radius of convergence here would be 3. Right, so here I'm going through a few examples of finding interval of convergence and then therefore radius of convergence after that. The first example is kind of the more simple, basic, I guess, no-brainer example you'd see when introducing power series. It's where the coefficients are all 1. So this is just the sum over x to the n. So it's 1 plus x squared and so on. And notice this is basically a geometric series with ratio x. And that only converges when, well, the ratio has absolute value less than 1. So this converges in this range here, basically because of the geometric series. Now, with that being said, the interval of convergence is this as an interval, which is negative 1 to 1. Because really what this says is that if you remember how to solve absolute value inequalities, it says that the inside of the absolute value x is in between 1 and negative 1. Now remember I said that we have to test for the endpoints technically. So it is possible we could have brackets here for both, or maybe just one and not the other. But in this case actually, when you plug in 1, you just get a sum of 1s, so clearly it's not convergent there. When you plug in negative 1 to the end, that diverges by test for divergence, because you have 1, negative 1, 1, negative 1, so it's not obvious what the last term will be, basically. So for that reason, there's also divergence there, so we don't include either of these endpoints in this case. And the radius of convergence is just half of this distance. 1 minus negative 1 is 2, so half of that's 1. Good. So now let's move on to this example here. So if you want to write out a few terms, we certainly can. So notice 0 factorial times x to the 0, that's 1. So I'm using the fact that the 0 factorial is defined to be 1 here. If you want to look into reasonings for that, there are really nice explanations out there. But this is more of a definition than anything. So this is what we're calling 0 factorial to be by kind of convention. So that's the first term. Plugging in 1 will give you 1 factorial x. Then 2x squared, and then 3 factorial is 6x to the third, and so on. Now to find the interval of convergence, like I mentioned previously, we're going to take, we're going to take the ratio test here. We're going to use the ratio test. So what does the ratio test say? The ratio test says that a series converges when the absolute value of the n plus 1 term over the n term is less than 1. So we're going to plug in n plus 1 here. So we're going to have n plus 1 factorial times x to the n plus 1 over plugging in n. It's going to give us this. And of course, you'll notice there's a little bit of cancellation. There's actually quite a bit of cancellation here. Notice here, these cancel straight up and we just get x. That'll always happen in the ratio test with any power series, as it turns out. Here, this part is not so obvious. But let me just kind of tell you that n plus 1 factorial is n plus 1 times n factorial, and then the factorials cancel out. So what we end up with here is the absolute value of n plus 1 times the absolute value of x. And we want that to be less than 1 in the limit as n goes to infinity. But now, as n goes to infinity, kind of funny enough, this will actually go to infinity unless x is 0. So the only time really this converges is when x is equal to 0. So this goes to infinity, let me say, except when x is equal to 0. For any other number, n plus 1 will go to infinity, and it doesn't matter what x is equal to. But when x is 0, then you just have a sequence of zeros which approaches 0. So in fact, in this case, the interval convergence is kind of a weird scenario where it's not really an interval, it's just a number itself. It's a singleton 0. And with that being said, the radius of convergence is the number 0 itself. So that's kind of interesting. But now moving on to something a little more tangible. For this example here, notice we have a center for this power series of 2. And we could, again, write out a few terms if you'd like. Let me kind of separate these. So if you want to plug in 0, you get this to the 0 is just 1. 0 factorial is 1. We saw that already. Plus, that would be x minus 2. Good. Plus, let me write it in parentheses, I guess. And then plus x minus 2 to the second over 2. And then you can write plus x minus 2 to the third. Kind of bring that back so I have a little more space to include that. There we go. Over 3 factorial, which is 6. And then on and on and on like that. Great. So we have an idea of what it is term by term. But now, how do we go from here? Again, we'll use the ratio test. So by the ratio test, we want to take the absolute value of the quotient of the n plus 1 term over the nth term. Now, to kind of skip some details, here's what I'm going to do. I'm going to replace all n's with n plus 1, just like this. Perfect. And then I want to divide this by, well, the general term with n's. So what I'm going to do instead is I'm going to multiply this, because our general term is a fraction in this case, by the reciprocal of the original one. So n factorial over x minus 2 to the n. And notice kind of what we saw here for the previous example still happens, only instead of with x, it happens with x minus 2. So there's cancellation of these powers, and there's only 1 left in the numerator. Here there's something similar that can be said. By the way, if you didn't like this explanation, you can actually write it out. So notice n factorial is n times n minus 1 times n minus 2 all the way down to 3, 2, 1. Maybe if that helps. Similarly, n plus 1 factorial is n plus 1 times n minus 1 times all the way down to 3, 2, 1. And what you'll notice happens here is that since these are in opposite parts of the fraction, the 1's cancel, the 2's cancel, the 3's cancel, they all cancel up to n. So, yeah, so that's completely gone in the numerator, so I'll write 1 in its place. And the denominator, we only have n plus 1 left over. Great. So now in total, we get this. We get 1 over n plus 1 in absolute values, multiplied by the only surviving member of the x minus 2 is just x minus 2 itself. So notice it looks very similar to what we had here. Basically, this was the base times some absolute value of some expression. But in this case, it's kind of quite the opposite. Here, this went to infinity, but here, as n goes to infinity, this limit actually goes to 0 no matter what x is. So these are kind of polar opposites in the sense that here this only converges when x was 0, here this converges no matter what x is actually. So this is always less than 1 for all x's. So in this case, the interval of convergence is negative infinity to infinity. And here when this happens, we actually say that the radius of convergence is then just infinity. Okay. So as it turns out, these two examples weren't anything usual, I guess you can say. They're kind of like extreme cases. Now let's take a look at something a little less extreme. Right, so for these set of examples here, we want to find the interval of convergence and radius of convergence. There are three, of course. For the first one, I'm not going to write out the terms anymore for these. You can do that on your own if you'd like. But more interesting for us is just using the ratio test straight up. So I know when using the ratio test, let me write, I guess I'll just write ratio test like this, RAT. Of course, you could use RT, but then that could be confused with the root test. So I'm going to use RA for ratio test. So for the ratio test, we're going to take the absolute value of this with n plus 1s over, so times the reciprocal of this with n's, kind of taking my advice from the previous example. Perfect. And you'll notice that, again, we have cancellation of x's, so that there's 1 left over on top. And what we have left over really is this absolute value of n plus 1 times the absolute value of x, like this. And in the limit, as n goes to infinity, this expression in the limit will actually approach 1 as n goes to infinity. Now, why that's the case, you can kind of review that on your own. You can use L'Hopital's rule if you'd like. Notice derivative of the top with respect to, I guess, n in this case, which sounds kind of funny, is 1, and derivative of the bottom is also 1. So it goes to 1 in the limit. You can also use domination, which I prefer to use. So if you ignore this 1 here, all lower powers of n, then this approaches n over n, which is 1. And you can also divide top and bottom by n. So there are different ways of arriving at this conclusion. But in the limit, this approaches 1 times the absolute value of x, which is just the absolute value of x. And by ratio test, to conclude convergence, we want this to be less than 1. So right away, what we end up getting for our interval of convergence really is the following. We get that x is in between, well, you know what, before I write it as an interval, let's write it like this. We get that x is in between negative 1 and 1. The only issue is, like I mentioned previously, we have to test the endpoints. Now, I'm not going to write it formally, but I'm just going to kind of say it out loud. When we plug in negative 1 in for x, notice we get negative 1 to the n over n. And that actually converges by alternating series test. So we actually get an or equal to here because negative 1 should be included in the interval of convergence because it converges there. However, when we plug in 1, something different happens. 1 to the n is just 1, and then plugging in 1, we get 1 over n, and the sum from n equals 1 to infinity of 1 over n is the harmonic series, which famously diverges. So from here, this is where I'm going to stop. And now I can write this as an interval. So for the interval of convergence, we have negative 1 to 1, just like that. And then with that being said, the radius of convergence is just going to be 2 in this case, half of 2 in this case, which is 1. So that's the answer here for this example. And that's kind of what we're going to do. In fact, this basically is what we'll do for all of these other ones as well. So again, I want to use a ratio test, so that's kind of like common to just jump into that. So now I want to, this is going to be a little more involved obviously, but if you plug in n plus 1s, we get negative 3 to the n plus 1, x to the n plus 1, over the square root of n plus 1, like that. And then multiplied by the reciprocal of this, which is the square root of n plus 1, over negative 3 to the n, x to the n. And yeah, you'll notice that there's quite a bit of cancellation here. These cancel, that cancels with one of these, well, with n of those. And all we have left now is -3. So let me write it over here. We have -3, I'll group it like this. So we'll have the absolute value of the square root of n plus 1 over the square root of n plus 1 is n plus 2 times the absolute value of -3 times the absolute value of just x. Now notice in the limit, as n goes to infinity, this part here will go to 1 by domination, because 1 and 2 are negligible, so you just get radical n over radical n, which is 1 in the limit. The absolute value of -3 is 3, so this actually just approaches this in the limit. And since we want a forced convergence, we want this to be less than 1, that implies that, well, the absolute value of x is less than 1/3 by dividing by 3. And this implies that x is going to be in between -1/3 and +1/3. And now all we really have to do is check the endpoints. Now, if you plug in -1/3, and again, I'll allow you to verify these details on your own, but if you plug in -1/3, -1/3 to the n and -3 to the n cancel out just outright, and we get 1 over radical n plus 1. Now, radical n plus 1, 1 over radical n plus 1, compares to 1 over radical n, which is 1 over n to the 1/2, which is a p-series where p is less than 1, which diverges. So I'm not going to write an or equal to for -1/3. For 1/3, however, when you plug in 1/3, in fact, I'll just kind of show that real quick. When you plug in 1/3, you end up getting this, in the numerator at least. And notice -3 to the n, you can actually split up as -1 to the n times 3 to the n. And this is actually a pretty important detail, because notice 1 over 3 to the n is the same as 1 over, well, 1 to the n over 3 to the n. Like this, we don't really need parentheses here. And the big reason I'm writing this, of course, is because you realize that these cancel, and we actually do get an alternating series now. So the numerator is going to be a -1 to the n after cancellation. The denominator is still going to be radical n plus 1, but notice since the denominator is increasing, the whole thing will be decreasing. It'll go to 0, and it's alternating. So by the alternating series test, it actually converges when x is equal to 1/3. So it's kind of the opposite of what we saw here. And let me just erase that work real quick. And now we can write our interval of convergence finally for this example as -1/3, 1/3, but close on 1/3 and open on -1/3. Perfect. And moreover, we can find the radius of convergence. What is the radius of convergence? Well, if you look at the length here, the length of this interval is 2/3, half of that is 1/3. And there's this really nice visualization we'll get. And I think, you know what, none of these actually have a center of non-zero. So it's hard to show here. But really the visualization you get is that the center of convergence kind of acts as the center of a circle. The radius of convergence kind of acts as the radius of a circle. So I said center of convergence. I meant to say center of power series. So it's kind of what's going to happen is that you have this real number line. You have your center, let's call it A, and you have your radius of convergence R. So you get to A plus R to the right, and then if you subtract R to the left, you get A minus R. So in fact, this will happen in general, and let me just kind of do some shading here. So we'll have a radius of convergence, and it'll actually be about the center. And again, I haven't really done too many examples where the center is non-zero here. But you'll actually see that'll happen in general. So, you know what, just to show that, I wanted to keep this one because this is actually a homework problem in disguise. But just to show that, let me make this x plus 2, if that's okay. So here the center will be -2. But yeah, so I'm going to actually use ratio test here. If you let the center be 0 like it was previously, then you'll see the homework problem. But for right now, let's just work with this and see what happens. So using the ratio test, I'm going to plug in n plus 1 instead of n. Plus 1 to the 4, 4 to the n plus 1. Just like that, okay? And then multiply by the reciprocal of it with just n's, so the original thing. So n to the 4th, 4 to the n, over x plus 2 to the n. And this, of course, is an absolute value because of the ratio test. So now notice, like usual, we get our cancellations. There's 1 left over on top for x plus 2. Here, they cancel in the opposite way, so we have 1, 4 left in the bottom. And then these don't actually cancel. The n to the 4th and n plus 1 to the 4th don't cancel. But we could still do some simplifying. So I'll write this as the following. So I'll have absolute value of n to the 4th over n plus 1 to the 4th like this. By the way, since they're both to the 4th power, a way I would like to write it better, I think, would be like this. You can take them both to the 4th power, and we can pull the power outside of the absolute value. So we can really write it as n over n plus 1 all to the 4th. And notice in the limit, this goes to 1 to the 4th, which is just 1. What else do we have left over? Well, we have a 4 left over on the bottom, and we have an x plus 2 on top. So let me write it as absolute value of 1/4 times the absolute value of x plus 2. Perfect. Now in the limit, this expression here involving n's goes to 1. So we're really left with x plus 2 in absolute value over 4. Because of course absolute value of 1/4 is just 4. And we want to force convergence, so I want this to be less than 1 for convergence. Multiplying by 4 gives us the following. It gives us the absolute value of x plus 2 is less than 4. Great. So what this really says is that our center is -2, which we kind of knew already because it's x minus -2 really. And it's less than our radius of convergence r, which in this case is 4. Now if you actually wanted to write this out, I don't have too much space, but I can kind of show here. If you wanted to write this out, you would say that x plus 2, the inside of the absolute value, is going to be in between 4 and -4. Okay, good. So now if you subtract 2 to both sides, just like this, what we end up getting is that x is in between, well, I guess 2 and -6. So that's going to be our interval of convergence, -6 to 2. But we need to test the endpoints. And in fact, I'll do that. I'm just trying to see if I have space. I guess I have space here. So what we conclude is the following. Our interval of convergence is -6, 2, like that. I don't know whether to use brackets or parentheses yet, but let me space it out a little better. There we go. I don't know to use brackets or parentheses yet, but we can test by just plugging them in for x. When x is -6, I'm sorry, we're on this one. When x is -6, we have -4 to the n. Notice -4 to the n is -1 to the n times 4 to the n. They cancel, and we get -1 to the n over n to the 4th, which converges by alternating series test. So -6 is good. Great. And when you plug in 2, you get 2 plus 2 here is 4 to the n. Those cancel. You get 1 over n to the 4. But 1 over n to the 4 is a p-series where p is bigger than 1. So this actually converges as well. So in this case, we actually saw one where it's bracketed on both of them, which is kind of nice. And what is the radius of convergence then? Well, I kind of already told you, it's just 4. And you can see that because the distance here, or the length of the interval rather, is 2 minus -6, which is 2 plus 6, which is 8. And half of that distance is 4. Great. So now I'm going to summarize the kind of last thing I explained here in a nice theorem that'll have 3 cases, and that'll be it for 11.8. Right, so I have this summary / theorem here. The book calls it a theorem, but it's basically a summary of what we've kind of concluded earlier. There's 3 cases. So the first case, so for any power series centered at A, the first case is that we have convergence only when x is equal to A. which by the way, when you plug it in, you just get a minus a, which is 0, so we have a sum of zeros only. We actually saw one example of this. The second case here is it converges for all values of x, so no matter what x is, it actually converges. Good. And the third case, which is I think kind of the more general scenario, this converges only when x minus a in absolute value is less than some number r, and diverges otherwise when the absolute value of x minus a is greater than r. And here I say r is some positive real number. Now, in reality, cases 1 and 2 are special cases of this. This is really when r is equal to 0, and this is when r is equal to infinity. So if you take r to be 0 and infinity, we get these kind of two cases. But since I said positive real number, and 0 is not positive, infinity isn't really a real number, then they're kind of all different cases here. But really this kind of says what the other two are trying to say. So we have really a radius of convergence is really what this is saying. And if you wanted to kind of go a little further and convince yourself why this happens, well, if you can kind of consider the ratio test, the ratio test says that we'll have Cn plus 1 x minus a to the n plus 1 over Cn x minus a to the n. We'll have cancellation, and we'll have the absolute value of Cn plus 1 over Cn times the absolute value of x minus a only. And we want to force this to be, well, less than 1. But there are a few instances of something happens, and it kind of depends. So really there are three cases for this part here in the limit. Either this approaches some number, you can call it 1 over r, for instance, and you'll kind of see what happens there. Or it approaches 0, or it approaches infinity. When this approaches infinity, the whole thing approaches infinity, except when x is equal to a, because in that case, well, this will make this this sequence be all zeros, okay? Or, well, this approaches 0, and when this approaches 0, then this is 0 for all x, because no matter what x is equal to, this will also be all zeros, so that converges then. And otherwise, if this just goes to, well, some other real number, and you can call it 1 over r, which I know sounds silly, then that means this thing will actually approach the absolute value of x minus a over r, where r is just some positive real number. And I know that sounds kind of funny, but again, since we're taking absolute values, it's going to be positive no matter what. Why I'm calling it 1 over r is, of course, because by a ratio test, we want to force this to be convergent, so I want it to be less than 1. So when that being said, so here r is just some positive real number. So with that being said, if x minus a in absolute value over r is less than 1, then we can multiply both sides by r and get the conclusion that we're aiming for from this summary above. So I know that part was kind of weird, but just kind of imagine this approaches, let's say, I don't know, 3, then you can call it 1 over 1/3. So that when you multiply both sides by 1/3, you indeed get that the radius of convergence is 1/3. So I'm just saying that you can always write any number as 1 over something, as long as it's not 0 or not infinite. Good. So that, like I said, really concludes 11.8. Really all we saw here was the introduction of power series, interval of convergence, radius of convergence, and that's really it. And notice we use ratio test and we tested endpoints. Good. So that concludes 11.8, and I'll see you in the next video for 11.9. Thanks for watching. See you then.